So very good morning to all of you, and today we'll be continuing in continuation to yesterday's problem. And what we were trying to apply non-degenerate perturbation theory to make certain calculations, and the problem that we had chosen, where we had introduced a perturbation of type beta delta x minus L by 2. And we had already calculated the first order correction in energy. The first order correction in energy. And now the next task that we have for this problem is to calculate the first order correction in its eigenvector. So we will be continuing from yesterday's lecture, where we have already calculated the first order correction to energy, in which what we have is we basically have a scalar potential, and in this scalar potential we have one-dimensional scalar potential, and what we do is we assume that the length of this one dimension is L, and we choose the dimension as x. And what we do is we introduce a small perturbation at the middle of this potential at L by 2. And what we are supposed to calculate is we are supposed to calculate the correction in the energy of this system. The first order energy we have taken, we can go for other orders, and the correction in its eigenvector, or the correction, the first order correction in its wave function. So proceeding from here, what we'll be doing now is, if we have to calculate the first order correction in the eigenfunction, that's given by sigma m not equal to n, then the expectation of psi m naught h prime and psi n naught divided by en naught minus em naught times psi m naught. So this equation we have already obtained this equation when we tried to develop the theory of non-degenerate systems, applying the Schrodinger's time-independent wave equation. So what we have here is we have to calculate this first order correction in the eigenfunction for the given problem, the problem in which we are introducing a perturbation, and that perturbation that we introduce is equal to beta delta of x minus L by 2. So in order to calculate this first order correction in the wave vector, we would like to calculate the expectation value of the numerator, and then we would like to calculate the difference between E10 minus En0. So proceeding from here, what we are going to do is we would like to calculate this expectation, that's psi m naught h prime psi n naught. And this will be equal to the integral from minus infinity to infinity, and you will have, because we already know that the eigenfunction for unperturbed particle in one-dimensional box is under root of 2 by L sine of n pi by L times x. So if this is the ket of psi of n, we can write down the bra of psi of m, and that will be the same thing, under root of 2 by L sine of m pi by Lx. So we can use the ket and bra here in this integral. So what we will get is we will have I would like to rub that first. So here I will have under root of 2 by L sine of m pi by Lx, and this will be multiplied to your perturbation, and your perturbation is beta times beta of the delta of x minus L by 2, and you will have sine n pi by Lx dx. So now what we can do, we would like to get the constants outside of this integration, and also we know that the limit of this integration will go from 0 to L. That's understood. So let's get out the constants. So I think the beta will be out, and under root of 2 by L whole square will be out. So inside will be left with minus infinity to infinity, and you will have sine of m pi x by L, and you will have delta of x minus L by 2, and you have sine of n pi x by L and dx. So in the similar fashion, we would like to use the property of the delta function. What we have is, if you have an integral from minus infinity to infinity, f of x and delta of x minus a, this is equal to f of a. So the solution of this integral can be written directly as, so we can write down, what we'll obtain from here is, we'll be obtaining beta is there, scattering group will cancel, so this is 2 by L, and the integral will come out to be as sine of m pi by L. For x, I will be using L by 2, and the another term will be sine of n pi by L. For the x, I'll be using L by 2. So this is going to give us the value of this integral. So I can say that the expectation of psi m naught h prime psi n naught will be equal to, this will be 2 beta by L, and this L and L will cancel, this L and L will cancel. What I will have is sine of m pi by 2 and sine of n pi by 2. So this is the result that we obtained for the numerator of our correction in the eigenvector. And the next important thing is the difference between En naught minus Em naught. And we better understand here, in this case, we have been correcting our wave function up to the first order. So in that case, this n will be equal to 1. It will be equal to 1. So this small n will be equal to 1. And we already know that the energy of the unperturbed system is given by n squared pi squared h bar squared by 2ml squared. So here I think I should not be using m here, this will confuse us. Let's take capital M for the mass of the particle. So this I will choose as the capital M because I'm using M as a subscript for another basis in the Hilbert space. So E1, so this is E0, so E1 of this 0 will be simply pi squared h bar squared by 2ml squared. This is how it will go. So similarly, you can think of Em naught. So this difference can be written as pi squared h bar squared by 2m, so m I'm using capital here for the mass of the particle, then you have L square, then minus of this will be simply m square, pi square h bar square divided by 2m L square. So we can get the common terms out, so this is pi square is out, h bar square is out, 2m L square is out, and inside we'll be left with 1 minus m square. So what we have calculated the expectation, and we have calculated this expectation, and we have calculated the difference between the first order energy, En naught and Em naught, and we can write down the correction. We can write down the correction, the first order correction, psi n1 as sigma. Now, as we know that m is not equal to n, but n here is equal to 1. So m is not equal to 1. And I will write down our expectation. What was that? That was 2 beta by L, and then sine of m pi by 2. And for n is equal to 1, I'll be using here only sine of pi. It will come up as sine of pi by 2. Okay, so this has to be multiplied by psi m naught. And this whole thing will be divided. It will be divided by this thing. Okay, En naught minus Em naught. So here I'll have pi square h bar square by 2. M has to be capital. So here m is the mass of this particle. L square 1 minus m square. Now this m, okay, this m is not equal to 1, and we better understand that we will have the value of this. We will have the value of every function only for the odd values of m. For even values of m, we are going to get zeros. So let's simplify it a little bit more to write down it in some chronological fashion. So what should I do is, I think this 2ml square will go up, this L and square will cancel, okay, and this 2 will go up, so this will make it 4. So I should write down this as equivalent to, so psi n1 can be written as sigma, okay, everything is defined here, m is not equal to 1, and you will have 4 beta L. In the numerator you will have 4 beta L, and in the denominator you will have pi square h bar square. So here you will have pi square h bar square, and then you will have your own thing, sine of m pi by 2, and you will have sine of pi by 2, and you will have the state psi m naught. So this equation is going to give us the correction, the first order correction in the energy eigenfunction. And we can see that we will have no value for even numbers, for even m, like 2, 4, and 6. This whole correction, there will be no correction, there will be no first order correction for even values of m. But if we choose the odd values of m, but what is important here is that m cannot be equal to 1. So you have to start your values from 3, 5, 7, and so on and so forth. And what we can do is we can expand, we can open this summation, and we can write down each and every term that will exist, and the summation of all these terms will give us the approximate measure of the correction of energy eigenfunction for this given problem. So with this, I think this problem is solved. We have solved this problem. We have calculated its energy eigenvector as a first correction to the energy. That was the first job that we did in solving this problem. And the next thing that we have done is we have calculated the correction to the eigenfunction. The correction to the eigenfunction to the first order. So this way we can proceed for more calculations. If we are interested in more calculations, we can proceed for more calculations, and the results we can every time have a correction, and that correction can be added to the unperturbed system so that we can have an approximate information about the system that has been subjected to an external perturbation. So with this, we would like to stop, and we will meet in our next lecture. And in our next class, we'll be talking about. We'll choose another problem basically to clarify our concept for solving the problems based on perturbation theory, and we'll choose a problem and we will try to solve that problem. So a very good morning to all of you, and today we'll be talking about, we'll take on our perturbation, we'll take on our non-degenerate perturbation to solve another problem, and that problem I'll be choosing is, I'll take the problem based on harmonic oscillator. So in doing, in first manifesting what problem we will choose, that we'll do in the course of time. But before writing down the actual problem and solving it, it is always advisable to have some basic understanding of harmonic oscillator. And when we talk about the harmonic oscillator, we have anything that oscillates and has periodic motion. We call it as a harmonic oscillator. And the problem of harmonic oscillator can be resolved classically, and at the same time we have the quantum description of the problem of harmonic oscillator. Now, if we think classically, if you think about the classical harmonic oscillator, the spring is the best example. If I have an ideal spring, I apply some force on this spring, and when I apply some force on this spring, there is increase in the length of this spring. So assuming that increase, if we assume that increase in length is x, then what we find is that if we have applied the force to this oscillator, the spring will exert a force opposite to the applied force, what we call as a restoring force. This restoring force is directly proportional to the displacement of the spring. Now, since we can see that the displacement is in the direction opposite to the restoring force, so a negative sign should be introduced between force and the displacement of this spring. So what we do here is we find that this F, the restoring force, is proportional to the negative of the displacement. Now, if this is the case, we can calculate the natural frequency with which this spring is going to oscillate, say up and down. And for that, we can think of force as as the mass of this spring times acceleration. And acceleration is the double derivative of the displacement. So for acceleration, I'm going to write d2x by dt2. So replacing this f by m d2x by dt2, you can write down this is equal to minus, introduce a constant k x. But this k is known as spring constant. So we are taking a basic mathematical module to understand a harmonic oscillator. So what we have the force. This force is directly proportional to the displacement. No doubt there has to have a limit. This relation is applicable within a limit. This is not a universal relation. That's why we have k. We have k different for different systems. So k is the spring constant. So I can write down this differential equation as, so this is m d2x by dt2 is kx. So I can take off this m and I can write this m here. So I'll have a second order differential equation d2x by dt2 minus k by m x equals 0. And I can write down this d2x by dt2 is minus omega square x is equal to 0. Now, the omega that has been introduced here is our angular frequency with which this spring is going to oscillate. And we can write down this omega as this omega squared is nothing but k by m. Now what is k? K is the spring constant and m is the mass of the spring. And you can write down this omega as under root of k by m. So if I have to write down the potential energy of this oscillator, the kinetic energy of this oscillator will be 1/2 of mv squared. If I have to write down the potential energy of this oscillator, what is that? That is 1 by 2 kx squared. So for k, I can use k from this equation, and the potential energy V will be 1 by 2 for k. I will have to square it on the both sides, so I will have omega squared, so m omega squared, so x squared is here. So this is our potential energy of the system. Now, what we subject over here in this problem is that this problem can be devised in two ways. One is classical and the other is quantum mechanical. So when we subject the problem of harmonic oscillator to the classical laws of physics, it predicts that this harmonic oscillator can have all possible energies. And that can be seen from this equation that you will have a parabola. And it will have all possible energies within certain limits, within the classical limits. You will have the classical limits, and within those limits, it will have all possible energies. And if we subject the same problem at microscopic level to the quantum mechanics, the results that we obtain, they are different than that of the classical harmonic oscillator. So for classical harmonic oscillator, you have the continuous energy. So your energy is continuous, and you have the limits. You have the limits, what we call as the classical limits. And you have all possible energies. But if we subject the same problem to the quantum mechanical laws, what we obtain that this harmonic oscillator can have only some discrete values of energy. It can have discrete values of energy. It can have energy 1, it can have energy 2, energy 3, energy 4, energy 5, and so on. And to have the energy of the type 2, it has to absorb some quantum of energy. And when it absorbs the quantum of energy, the harmonic oscillator can move from the state 1 to state 2. And it can move from state 2 to state 3. This is not a classical physical type of transition that's taking place here. Your harmonic oscillator will absorb a quantum of energy and it will appear to have an energy of the state 2. Then it may absorb another quantum of energy and it will have an energy of state 3. Or it can emit a quantum of energy. If it emits a quantum of energy, it can come down to a step down by virtue of its energy. So what is happening here is, for the classical harmonic oscillator, you have all possible energies that are linked with your harmonic oscillator. But when you talk about, when you subject your harmonic oscillator at atomic scale with quantum mechanical laws, you find that this harmonic oscillator will not have all possible energies. It will have only some finite energies, which it can be in those states. And another important difference here is, for classical, if we think about this harmonic oscillator in terms of temperature, if I take down the temperature, if I assume taking temperature down to 0 Kelvin, the classical harmonic oscillator will cease its motion. It will not carry any kind of energy at all. But at the same time, if I take on my quantum mechanical system and take my temperature to absolute 0, my quantum mechanical harmonic oscillator, if the temperature that's obtained is 0 Kelvin, it will still have a finite energy, what we generally know as the 0 point energy. So the point is that in quantum mechanics, when we have to treat a problem like this, where we are dealing with a quantum mechanical harmonic oscillator, we have an approach of using operators known as creation and annihilation operators. So what a creation operator does, it takes my harmonic oscillator from one quantum state to another quantum state. And what an annihilation operator does, so what we have is, we can think of using creation operators, and we can think of using annihilation operators. And using these operators, we can move our system quantum mechanically from one quantum state to another quantum state. So for making use of a creation operator, you are taking your quantum system from one state to another state. You are increasing the state for your quantum system when you think of using a creation operator. And when you think of using an annihilation operator, what it does, it basically takes your system down. It takes your system down by 1. So these operators, they play a very key role in understanding the problems of harmonic oscillator at the quantum level. So if I have to write down a creation operator, a creation operator can be symbolized as a dagger. This is our creation operator. Creation operator. And we can think of another operator which is known as annihilation operator, that is A. So A is our annihilation operator. Annihilation operator. Now, from the basic theory of quantum mechanics, we understand the values of these operators. If I have to write down A, which is my annihilation operator, this A is m omega by 2h bar raised power 1 by 2 x cap. This x cap is the position operator. Then plus iota 1 by 2m omega h bar raised power 1 by 2, and here I have the momentum operator. So this is my annihilation operator. And I can write down the creation operator from this equation. All I have to do is to take the dagger, and for dagger what I have to do is to change the sign of the complex part of this equation. So if I have to write down a dagger, which is a creation operator, that will be equal to m omega by 2h bar whole raised power 1 by 2. Then here you will have x cap minus I 1 by 2m omega h bar raised power 1 by 2 p cap. So you have two equations. One is for the annihilation operator, A, and another is the creation operator, which is a dagger. And we can see if I add the two equations, suppose this is my equation 1 and this is my equation 2. If I add these two equations, these two terms will cancel. If these two terms will cancel, I will get what I'll get. I'll get A plus a dagger and 2 times this. So what will I get? I'll get A plus a dagger is 2 times m omega by 2h bar whole raised power 1 by 2 x cap, where x cap is our position operator. This is our position operator. This is our position operator. All right, so I can think of taking this 2 inside the brackets. So A plus a dagger will be, it will be 4m omega by 2h bar raised power 1 by 2 x cap. And we can immediately see that this 2 and 4 will go. And what we will obtain here is, we'll obtain here A plus a dagger will be equal to 2m omega by h bar raised power 1 by 2 and x cap. And from this equation we can calculate the position operator. So x cap will be it will be 2m omega by h bar whole raised power 1 by 2 times a plus a dagger. So this is my position operator, and I can use this position operator to solve some of the important problems in quantum mechanics. And I think with this I would like to stop because they have to take another class. Okay, you can come in. So I'll stop here. I'll continue this lecture from this in our next class. So thank you. Very good afternoon to all of you, and I hope everybody is fine. And in this lecture, we'll take on the problem that we had taken in the previous video. And in fact, I gave you the introduction to simple harmonic oscillator problem. So the point was that I started from the operators. One is creation operator, and another one is annihilation operator. And annihilation operator. So for annihilation operator, we have A as an annihilation operator, and this is equal to n omega by 2h bar raised to power 1 by 2 x cap plus 1 by 2 omega h cross raised power 1 by 2 p, where this x is the position operator, and p is the momentum operator, m is the mass of the oscillator, omega is the angular frequency of the oscillator. So A is representing the annihilation operator, and if we have to write down the creation operator in this context, the creation operator will be at a dagger, so that will be, did I keep iota with it? I forgot to write down iota here. So this is plus I. So for a dagger, we'll have m omega by 2h bar raised power 1 by 2 x cap minus I 1 by 2m h bar omega raised power 1 by 2 p cap. So as we proceed, we calculate, we add the two equations. What we get is a plus a dagger. So this part will cancel. Once we add the two equations, this part will cancel with this. So this part will be added, and what we will obtain is, we'll obtain 2 times m omega by 2h bar raised power 1 by 2 x cap. And we can take this 2 inside the brackets. So inside it will be 4 m omega by 2h bar raised power 1 by 2 x cap. So in the left hand side, what we have is a plus a dagger. So this is 2 1s are, this is 2 2s are. So what we obtain is, so from here we can calculate x cap, we can have an expression for the position operator. So the position operator x cap will be, so this h bar will go up and 2m omega will come down. So this is h bar by 2m omega raised power 1 by 2 times a plus a dagger. So this is our position operator, and a comma a dagger, they are respectively the annihilation operator and creation operator. Now the point is that when we act upon the eigenstate of the system by these operators, now if I take a dagger as my creation, this is the creation operator, and let's assume that it acts on the state psi n. So once this creation operator acts on the state psi n, what it will do is it will reflect to you n plus 1, and your state will go up by 1. So acting your creation operator on the state psi n will take the state psi n to the state psi n plus 1. Now, if I act my annihilation operator on the system that I have here, what I'll get. So I can think of using the annihilation operator on the state psi n. What it will do is it will take down our state 1 step down. So if I choose this as my original state and acting psi n plus 1 my original state, what I'll come up with is I'll get under root of n plus 1 minus 1, and my state will move from psi n plus 1 minus 1. So I will have a psi n plus 1 will take me to under root of n psi n. So we can literally take these two creation and annihilation operators, and they can be utilized in such a way to move from one state of the system to another state of the system. No doubt, it's clear to us that it is basically the absorption and emission of the quantum of the energy by the harmonic oscillator that takes our harmonic oscillator from state A to the state B. Now let's try to explore this thing and let's try to solve a problem based on these operators. And the problem that we will try to solve is certainly based on perturbation, and we choose non-degenerate perturbation theory, and we have the ideal unperturbed harmonic oscillator. We know its energies, and then what we do is we introduce some perturbation to the harmonic oscillator. Now, if I start with the problem that I have H, the resultant is the H naught plus H prime. Well, this H prime, I will choose this H prime to be, say, something like beta x. So all we have to do is to calculate the correction. So we are introducing this perturbation to the original Hamiltonian. So previously we were dealing with a harmonic oscillator where we only have two important terms: potential energy term, ideal potential energy, ideal kinetic energy, and then we add up an additional disturbance. What makes the transition of this harmonic oscillator, it basically makes the transition of your system towards an harmonic oscillator. So this perturbation that we introduce in our system, it turns out our ideal harmonic oscillator problem into an harmonic oscillator. An harmonic oscillator. So what I wish right now is I want to calculate the correction. I want to calculate the first order correction. That would be the right choice. First order correction. First order correction in energy. I'd like to go with the first order correction in energy for a harmonic oscillator where we introduce a perturbation of beta x. So how do we calculate the first order energy correction to our system? So if I write down En1, this will give me the measure of the first order correction to my problem. What is that? That is psi n naught H prime psi n naught. So I can think of simplifying this problem by using the state 0, and for H prime I have beta x cap and taking this state as the state 0. So this will give me the correction in energy for the perturbation that we have introduced in our system. Now let's try to calculate the first order energy correction. All I have to do is to calculate this expectation value, as we have already calculated this x cap. What is this x cap? This x cap is, what is it? It is, we check it out. So it is h bar by 2m omega raised power 1 by 2. So let's put down that. Come on. It's very fuzzy over here. So what should I write here is h bar by 2m omega raised power 1 by 2. A plus a diagonal. So what I'll do is I'll introduce this operator in my expectation value. So what will I get? I will get En1, that will be 0, and then I will have h bar by 2m omega raised power 1 by 2. I have original beta with it, and then I will have a plus a dagger for it. I will close it with the state 0. So I can get beta out h bar by 2m omega raised power 1 by 2. So I'll be left with the state, the bra of 0, and inside I'll have a plus a dagger of 0. Now, all I have to do is to calculate this. Okay, so we can write down this is, I will write this again. This is beta h bar by 2m omega raised power 1 by 2. So here we will have 0a and 0 plus 0a dagger 0. Now, you are acting on a system with your state 0 and you are using an annihilation operator. So this thing will immediately come out to be equal to 0. And here we are using the creation operator on the state 0. It will change to the state 1. So what we will have En1 will be beta h bar by 2m omega raised power 1 by 2 times 0 plus, you have the state 0, and you will act your creation operator on the state 0. That will convert it into the state 1, and outside you will have under root of 1. Now, as we know, if we have a situation like psi n and psi n, such that n is not equal to m, then the result that you obtain from here is 0. So the same thing can be used here, so this result will be equal to 0. So the first order correction to the perturbation that has been introduced to the harmonic oscillator will be 0. There will be no change in the first order energy of this harmonic oscillator because you have to multiply it by 0. So this En1 is going to be equal to 0. Now, so that means this is giving me an indication if you have a problem like this, any perturbation that you introduce, which is odd in nature, will give us 0 first order correction in terms of energy. There might be the second order corrections that can be calculated for the system, but one thing is clear that when we encounter the things like beta x cubed, beta x raised power 5, the first order correction in those categories should give us what we call as 0. Now let us choose the perturbation of type for the same harmonic oscillator as beta x cap raised power 4. Now let's solve this problem and calculate the first order correction in the energy of the system. So let's have that target. So how will we do that? As we know, what we do is to calculate the first order correction in energy, we will have a state like psi n naught, then we will have beta x cap raised power 4 and psi n naught. So solving this equation will lead us to the result in calculating the first order correction to our harmonic oscillator, which has a perturbation that has been introduced in the form of beta x raised power 4, where beta is a small number. So we will use the same technique which we used for the previous problem. So En1 will be, so instead of sine 0, I will choose 0. And for beta is beta. For x raised power 4, it will be x h bar by 2m omega whole raised power 1 by 2. But there is a whole power of x, and that power is 4. And what else is a plus a dagger raised power 4 and go back to the state 0. So this is the result. And what will be out from this equation? I think beta will be out. This square, this 2 and 4 will cancel, so we'll get 2 here. So what will be left here is h bar by 2m omega raised power 2. And inside, what we are left with is the 0, the bra of 0, and a plus a dagger whole raised power 4. Then again we have the state 0. Now, see, what is important here is that we have, once we make the multiplication, we have to take the sequence, the same kind of sequence has to be taken while multiplying all of these operators. What I'm telling here is, so what we have beta h bar by 2m omega square, this will give us 0, and then what we will have a plus a dagger multiplied with a plus a dagger multiply a plus a dagger, then again multiply a plus a dagger, then close, and then you'll see. Now, obviously we can understand, since you have raised power 4, once you make those sequential multiplications, we will have 16 terms. 16 terms will come out on multiplying these brackets. And after having these 16 terms, 14 terms will give us 0 result. I mean, 14 terms. The 14 terms that you will get, they will lead us to 0. And the only 2 terms that will exist while you make this multiplication, the 2 terms that will stay is en1 will be what we have. We have beta, we have h bar by 2m omega raised power 2 times. The first term that we will have will be a dagger and a dagger, and another term will be a dagger, a dagger. These 2 terms will exist. The rest of the 14 terms, if you're interested in doing those calculations, you can do them. The rest of the terms will lead us to 0, and we'll be left with only these 2 terms. So the target is here to calculate these 2 terms and to have the first order correction in energy for the given harmonic oscillator, while we have introduced the anharmonicity to the system of whose nature is like beta x raised power 4. So this is my equation. Now let's calculate these expectation values using these creation and annihilation operators. So what's going to happen here? I will keep this thing as is. I will call it zeta for the time being. So in brackets, I will have the first term 0, then I'll have a dagger, and the state 0. So this will be one term, and the term will be 0. Then I will have a dagger, and then I will have 0. So this is what I am entrusted to calculate now. This zeta is being replaced by the whole set of constants that are in this bracket. So let's proceed from here. Let's move on from here. The very first term will be, the first term that we have is a dagger and a dagger, then closing. Okay, so we will have the first operation taking place on the state 0. What we will get out of it? So first of all, under root of, because here we are executing the creation operator. The creation operator will take our state one step ahead, and outside we will have here under root of n plus 1, so that will be 1. So inside what will be left with 0, a dagger, and this state is gone to the state 1. Now, let's make another operation. Now, I have another a dagger acting on the state 1. Now, what this dagger is going to do, I have under root of 1 here, so this dagger will create me under root of 1 plus 1, because n is 1, so n plus 1 will give me 2 here. So I'll be left with 0, 1, A, and this 1 will go into the state of 2. Okay, so till now, I think it's okay, it's fine. So what we're left with, we're left with under root of 1, under root of 2, and then we'll make another operation. We'll make an operation of A, which is an annihilation operator. I think I should run this. So what we have is we have the annihilation operator, and one annihilation operator will act on the state 2, and it will convert it into the state 1. And what will be outside will be under root of 2. And now we are left with the last operation in this. That will be under root of 1, under root of 2, under root of 2. And acting upon this annihilation operator on the state 1 will change this state 1 into the state 0. And here I will have under root of 1. So what will be the result will be 0 and 0. So this is as equivalent as psi n 0 and psi n 0, and this result is equal to 1. So the answer that we'll get for this part of the problem is under root 2 whole square. Square root will cancel and you will get 2. This is the first thing. Now we have another expectation value that's to be calculated. What is that? The next one we have is 0, a dagger, a dagger, and 0. So the first action that this creation operator will take on this state 0, you will have simply under root of 1 for this, and then you will be left with a dagger, and this 0 state will convert into the state 1. This will be the first thing. Another thing is that annihilation operator. This annihilation operator will act on the state 1. Again, you will have under root of 1. Then you will again have under root of 1. And then this will be 0, a dagger. Now this 1 will go back to 0. And we can think of the same thing as repeating. And what we will get here is we will have under root of 1 times under root of 1 times under root of 1 times under root of 1. And the last thing that we will come up with is, because when we will take on a dagger on 0, it will make a transition to the state 1. Then again, when we will be using the annihilation operator, it will take a transition back to the state 0. So you will have 0 and 0 here, and this is equal to 1. So the overall result here that will be obtained is equal to 1. So finally, we have calculated the first order correction for this problem. En1, beta is outside. You have h bar by 2m omega raised power 1 by 2, which I have chosen as equivalent to zeta. And then inside the brackets, for the first expectation value, we had the answer of 2, and for the next one, we had an answer of 1. So the correction in the first order correction to this and harmonicity that has been introduced to the ideal harmonic oscillator problem is equal to beta times h bar by 2m omega raised power 1 by 2, and this 3 will be outside. So this is how we can calculate the corrections, the corrections to the energy that are introduced by subjecting our system to the small perturbations. And in this case, the system we were dealing with is a harmonic oscillator, and this harmonic oscillator is subjected to an external perturbation, and that perturbation is calculated in the framework of what is already calculated in terms of the original harmonic oscillator. So with this, I think this problem is over, and you can go on solving the same kinds of problems to actually calculate the corrections in terms of energy and in terms of eigenvectors for the problems based on perturbation theory that's being utilized, that's being experienced to calculate the corrections in these systems.